There is some big space news coming in the next year. It'll be on the front pages of the newspapers and all over the internet, because if everything goes according to plan, we will be getting the first ever picture of a black hole. Physicists calculated centuries ago that an object with enough gravity could trap even light. But black holes have been hard to observe up close because they're either too small, too far away, or both.
To see the supermassive black hole at the center of our galaxy, it would be like taking a photograph of a DVD on the surface of the moon.
The mass of the Milky Way's central black hole is over 4 million times greater than our sun, but its diameter is just 17 times larger, and most black holes are smaller than that. That's why every image you've seen of a black hole up close, well, those are illustrations made by artists. But if astronomers haven't observed black holes directly, why are they fairly certain that they exist? Well, they've observed the effects of black holes on other things, like these stars at the center of our galaxy.
So this is a time lapse of over 16 years worth of observations of stars near the center of our Milky Way galaxy. And it's been sped up by a factor of some 32 million times. So this is a lot of time over just a couple of seconds. And what it's showing is that these stars are seemingly orbiting something in the center of our galaxy.
The only known object that could cause those orbits, and that would be so small, is a supermassive black hole. Another way to spot black holes is by the glowing material spiraling toward their event horizon, or the point of no return. Friction heats this matter up tens of millions of degrees, and anything that hot emits X-rays that we can observe. Here's a pair of galaxies that pass through each other. There are at least 9 small but active black holes here, but you can only see them when you look at the X-ray layer. And these dots are X-ray sources from supermassive black holes at the center of galaxies 3 to 10 billion light years away. And that's just from this small patch of sky. Some supermassive black holes also shoot off gigantic jets of particles at nearly the speed of light, seen here in radio wave data from the galaxy M87, which has a much, much bigger black hole than the one in the center of the Milky Way.
Sometimes black holes at the center of galaxies can shoot off jets of material that are larger than the galaxies themselves.
The jets don't come out of the black hole. Rather, they seem to result from nearby matter interacting explosively with the spin of the black hole. No other known source of energy could power these things. Over time, these jets create huge lobes of particles that glow in radio waves but aren't visible in optical light. You can see them surrounding this galaxy cluster 2.6 billion light years away. The X-ray layer shows how the jets from the black hole in the central galaxy displaced some of the hot gas nearby. And just to give you a sense of how big this is, our entire galaxy could fit several times over inside these gas cavities. The historic first picture of a black hole won't be of one of these superactive monsters, though. They're targeting our own black hole at the center of the Milky Way, which flares up occasionally but is relatively quiet.
And they're doing it by creating what's called the Event Horizon Telescope, which is this worldwide effort to kind of link up a lot of different radio telescopes around the world.
They're looking at radio waves rather than optical light so that they can see through the thick clouds of gas and dust near the galactic center. The researchers will correlate the waveforms from the distant telescopes to boost the signal and quiet the noise. There's so much data involved that it has to be flown on airplanes, but once it gets translated into an image, they expect to see a dark, round silhouette surrounded by bright matter swirling around the event horizon, and it'll be brighter on the side where the matter is moving toward us. And if they see something else entirely, well, that could be even more interesting.
What I can say here is that I don't know what we're going to see. By the way, that's a disclaimer about all of this. I have no idea what we're going to see with this, right? Which is part of the reason we get up in the morning, right? Because if we knew what we were going to see, it would be engineering. But the reason it's science is because we don't know, but what we can put ourselves in a good position to do is to have high signal-to-noise ratio data. And that is what I am increasingly convinced that we're going to have.